Okay, I think it's 4:01. Hello, everybody, and welcome from Berlin to today's ENLA seminar. So this is Jörg Liesen, and I'm wishing you a good afternoon, morning, or evening, wherever you are. I'm happy to introduce today's speaker, Yuji Nakatsukasa from the University of Oxford. Yuji is well known for his work in numerical linear algebra, in particular eigenvalue perturbation theory, matrix functions, matrix analysis, and randomized linear algebra. And the second focus of Yuji's work is in polynomial and rational approximation theory, and definitely also practice. His papers usually contain algorithms, codes, and/or insightful numerical examples, and are always beautifully illustrated as well. Special feature of Yuji's highly original contributions is the combination of the results and techniques from these diverse areas. And so metaphorical, we could think of Vandermonde plus Arnoldi. And this is actually the title of one of his recent papers written jointly with Pablo Brubeck and Nick Trefethen, which is to appear in SIREV Review, and which Nick Trefethen actually presented in the ENLA seminar in June. So Yuji is a recipient of the Leslie Fox Prize in 2011 and the Householder Award in 2014 for his PhD thesis, which was written, or he wrote under the supervision of Roland Freund at UC Davis. Before handing over to Yuji, I would like to mention that all participants, as usual in today's seminar, can ask questions during the talk in Zoom or YouTube's Q&A. And these questions are handled today by Valeria Simoncini and Milia Freitag. And now, Yuji, please go ahead with your talk on fast and stable randomized low-rank matrix approximation. The floor is yours.
Great. Thank you so much, Jörg. That was a very warm welcome. And thank you very much to everyone in the organization for organizing this seminar series. I think this has been one of the best things that's happened over the year in this community in these difficult times. So I really appreciate the invitation and the opportunity to be part of this. So I wanted to talk about my recent work about fast and stable low-rank matrix approximation. And I wanted to start with something that I think everybody in the audience might know. If not, then this is going to be the most important thing that I will say today. And I like to call this the most important result in numerical linear algebra. So it's about low-rank approximation of a matrix. So suppose you have a matrix that's big, and then very often there is a reason that it'll be great if we can approximate it with a low-rank matrix or low-rank factorization, which is basically a product of the form where one matrix is tall and skinny, the other matrix or matrices are fat. Sometimes there's a core matrix inside. But the point is, once you have a factorization like this, the data will be compressed. There's more information that can be extracted easily from this factorization. So there are many benefits from having a low-rank approximation, if that's possible. Of course, not every matrix is low-rank approximable, but there has been a lot of work that shows in these cases, the matrices are going to have low-rank structure, or sometimes hidden low-rank structure, like off-diagonal part is low-rank, and so on and so forth. In this talk, I'm going to just assume the matrix itself is low-rank approximable and try to come up with a good algorithm to compute it. And for this low-rank approximation, there's a classical optimal solution, which is just a truncated SVD. You take the SVD, you take out the leading parts of the left, right singular vectors and the singular values. Let's just say we take the R parts of it, and then you form this outer product to form a low-rank approximation. And so that is known to be the optimal solution in the sense that the difference between the original matrix and the low-rank approximation is the smallest possible in any unitarily invariant norm. And there's a complete proof. The only reference that I really know of that really shows the complete proof for any unitarily invariant norm is this classical textbook by Horn and Johnson on matrix analysis. So this is all great and beautiful, but The issue here is that the cost of computing a truncated SVD, if you want to do it exactly, then that will be the complexity is cubic in the dimension. So it's m times n squared, where I think I'm assuming m is larger than n. So this is not a fundamental assumption, but I think I will make that assumption throughout. So if we think of m and n in the millions, this quickly becomes infeasible. So we would like to look for cheaper approximation. So we don't necessarily have this optimal approximation, but we're going to live with something that's suboptimal, but still a much faster approximation. So that would be a feasible computation. And one thing I would like to note, in this talk, I'm going to try to find an approximation of the form of this tall, skinny times fat matrix. But I don't impose any structure in any of the components. So here you have orthonormal matrices, U and V, but that's not going to be the case in what follows. So in order to get a cheaper SVD or approximate truncated SVD, a very successful idea in numerical linear algebra has been randomization. And one of the most successful part of randomized linear algebra has been randomized SVD. And in particular, this paper almost 10 years ago by Halko, Martinsson, and Tropp has contributed significantly to the analysis and therefore the popularity of this randomized SVD paradigm. And then the algorithm is actually very simple. The analysis is by no means not simple. But the algorithm I can summarize in just 4 lines of code or pseudocode. So the way it works is you start with a tall, skinny random matrix. Where this is, so R is a given number that you think is going to give a good approximation. So rank R approximation is going to do a good job of approximating the matrix. But here is an M by R matrix, random entries. You compute A times R, A times X, and then take the QR factorization of that matrix. And then this Q matrix is somehow the magical matrix in the sense that if you project the matrix onto the column space of Q, then you get a brilliant approximation in the sense that this is a low-rank approximation, or low-rank matrix at least, but it's going to be a great approximation in the sense that, so A hat is going to be Q transpose A. The difference is within a small kind of constant times the best possible, up to a small difference in rank, but let's not worry too much about it. So basically, it's saying that this is already doing almost an optimal rank R approximation to the original matrix. So so this is great. And if you actually do this, which it can be done in like 5 lines of MATLAB code, it really just works. And the probability of something getting an error that's significantly larger than this is exponentially small. So it really just works, and it's an amazing algorithm. The cost of this algorithm, as presented, will be mnr. So that's definitely much smaller than mn squared. But sometimes we can improve it further by using an FFT technique and interpolatory decomposition, although this comes with the slight worse accuracy. I would like to highlight at this point this blue term that I have here, which is mr squared, which comes from the orthogonalization step here. So in order to orthogonalize an m by r matrix, you need mr squared operations. And this is a part that I'm going to try to kind of reduce in this work. OK, so that's randomized SVD in HMT's way. So I'm going to call this algorithm HMT, and this is going to come up many times in throughout this talk. So another key component is Nystrom's method. So this is another randomized SVD method applicable only to positive semidefinite matrices, so symmetric positive semidefinite matrices. And then the way it works is really simple. So you draw a random matrix, tall, skinny matrix, and then you just form this approximation. And surprisingly, this matrix, this approximation is also very good. And even more surprisingly, perhaps, is an observation made in HMT, the classical paper, that says, if you take the Q matrix that was used in HMT, recall that HMT takes Q transpose A as the approximation. But if you use this Q to just plug in X equals Q, then this will be another approximation, the Nystrom type approximation. I'm going to call it Nystrom plus HMT. And this is going to be a really, really good approximation, even better than HMT. So here's an illustration using experiments. So I took a 50,000 by 50,000 positive semi-definite matrix, and then I'm running HMT on this method and Nystrom. So you know immediately that note that this is a log scale time scale. So the difference here is like a factor 10. So Nystrom is incredibly fast compared to the competitors. And Nystrom plus HMT is slightly faster than HMT. In terms of accuracy, the first thing to note, so the black line or curve is the SVD. So this is the best possible with the truncated SVD. So anything that's close to it will be, well, near optimal. The first thing to note is everybody's doing pretty well. And in particular, Nystrom, even though it's so fast, is doing, I would say, decent job of tracing how the singular values are decaying. Here, the exact singular values are decaying exponentially. And then all the methods in some sense is doing very well at approximating, at finding rank R approximation for varying numbers of R. And maybe I would emphasize that Nystrom plus HMT is getting the closest to the SVD. Right, so having done this experiment, this makes you wonder, well, basically it raises kind of two questions. The first one is, since Nystrom is so fast and accurate, but it's only applicable to positive semi-definite matrices, it sounds like a shame that you can't get the same benefits and apply it to general matrices like rectangular matrices. So can we not generalize this method somehow to non-symmetric and rectangular matrices? That's the first question. Another question I have not mentioned is the presence of the pseudo-inverse. So note that there's a pseudo-inverse here. And as a numerical analyst or a hardcore numerical linear algebra researcher, and whenever I see an inverse, I get a little bit worried. And it's alarming in terms of the stability. So if you actually compute this, for example, if you actually compute the pseudo-inverse and multiply it to form this approximation, you really get rubbish. And that's because this matrix is really ill-conditioned. In some sense, if it's not ill-conditioned, then this approximation is going to be a poor approximation. So for this approximation to be a good approximation, this matrix in the middle has to be ill-conditioned. So the numerical stability becomes a serious issue here. So does this pseudo-inverse cause instability, or is there a way to implement this pseudo-inverse in a stable manner? These are the two questions that arise naturally. And so here's the answer to these questions. So in some sense, the happy answer. So we can generalize this Nystrom's method to general matrices. Number two, it is going to be stable. So if you implement it in an appropriate manner, in a way that I am going to describe later, then this generalized Nystrom, which is the name that I gave, so the generalized version of Nystrom applicable to general matrices is going to be just stable. So if you look, so here's an implementation. So I use the same matrix and applied this generalized Nystrom. The runtime is about twice as much as that of Nystrom, which kind of makes sense because we're dealing with potentially non-symmetric matrices. The accuracy is, as you can see, it's more or less the same as the other ones. It's slightly better than Nystrom here, somewhere between Nystrom and HMT. But the point is, it's good accuracy. It's very good speed. So I'm going to try to explain what is done in this generalized Nystrom approximation. And here it is, basically. So you start with Nystrom. You try to kind of modify it in such a way that it will be applicable to general matrices. And you immediately see that you have to change one of the x's. So let's change x to y. And so because we're talking about potentially rectangular matrices, there's no way for the same size of x and y to work. But once you do that, and then you make a natural modification in the core matrix, which is matrix here, which is a small matrix, this is the approximation that we are going to use. So just a visual illustration, this is a tall skinny matrix. This is going to be a small core matrix. This is going to be a fat matrix. One thing that I would like to emphasize now is that the number of samples in terms of x and y do have to differ to guarantee stability. So in other words, if we're going to take our columns, our rows in our columns in x, then we need to take r plus L columns in y. So and then L needs to scale proportionally to r. I'm going to explain this later, but this is going to be important. Many previous studies take the oversample number to be like constant, but that's not necessarily going to work, especially when the rank is large. And then this approximation, I'm going to show, well, this is reasonably easy to see. It's single pass in the sense that you don't have to revisit the matrix. And it's near optimal cost for example, for dense matrices, the cost I'm going to show you later. I'm going to show you that it's going to have a near optimal accuracy, essentially comparable to those of HMT and Nystrom. So what about stability, which I haven't addressed yet? So that's the key component of this work. This is probably the main contribution from a technical side of this work. So we do need to make a slight modification to this expression. So that is this epsilon pseudoinverse. So instead of taking just simply the pseudoinverse, we're going to take this epsilon pseudoinverse, which is basically this. So if there's a singular value that is smaller than epsilon, and then we ignore that part, and then take the pseudo-inverse of corresponding to the singular values larger than epsilon. So that's the formula for the epsilon pseudo-inverse. If we do this, and I'm going to call this the stabilized generalized Nystrom method, sometimes SGN. This is going to be a stable method, or there is a numerically stable way to implement this approximation. Right. Okay, so this expression is going to be the key expression throughout this work. And one thing to note maybe here is that you can write this as a projector onto a certain subspace times x times a, or acting on a. You can also write it as as another projector. You can also write it as a times another projector, which will turn out later. So this is a projector for general matrices M, which is tall skinny, N, which is another tall skinny matrix, but it's transposed, so it's fat, in a core matrix. So this you can see is a projector in the sense that if you square it, you get the same thing. So this expression, this overall expression, turns out to encompass many of the previous work in randomized linear algebra. So in particular, many of the algorithms, for example, HMT, you can think of it as a member of this family of approximation, even though it probably didn't look like that way. And I can try to prove that briefly here. So HMT does this, where Q is the orthogonal factor of A times X. But if you choose Y to be AX, then you get, what will happen is that this projector becomes an orthogonal projector. And then this orthogonal projector is simply Q times Q transpose. So there you go. We get exactly this matrix obtained by HMT. So there is a choice of X and Y for which you get HMT. Nystrom is almost obviously a member of this family, because if A is symmetric positive semi-definite, you can take X equals Y, and you get that will reduce to Nystrom. Two methods that I would like to highlight here and maybe in the next slide is one by Clarkson and Woodruff, which is the first paper to basically show this expression for the purpose of doing randomized SVD. They were using X and Y to be count sketch matrices, so-called count sketch matrices, which are a matrix of lots of zeros and some ones. A consequence of which is that sometimes you are going to need a slightly larger R to guarantee a good approximation. A follow-up work is one by Tropp, Strever, Udell, and Stever, which basically does this, really. So almost literally does this, but they kind of are concerned about stability a little bit. And what they do is they do a QR factorization of A times X. Somehow, in order to avoid the inversion or pseudo-inversion of this ill-conditioned matrix. So if you do this, it turns out that the matrix that you need to invert becomes well-conditioned. So therefore, they somehow overcome the potential instability. But again, in exact arithmetic, they're doing exactly this. And a part of this work is is to show that that kind of stability through the QR factorization is actually necessary, because there is a way to do it without it in a numerical stable way. So I list here some more algorithms that can be written in this form, but I guess I wouldn't go into details here. And a little bit more about generalized Nystrom. Once again, this is the expression, and I would like to maybe mention the so-called Wedderburn formula, which I've been made aware of by Alex Townsend recently. So this is a very classical result in numerical linear algebra or linear algebra, and this is actually precisely the Wedderburn formula when there's zero oversampling going on. And then immediate consequence of that is that, for example, A minus this approximation is going to have strictly lower rank. So the maximum rank that I can take is going to be m minus r. So there's a cool connection to very classical results. And so once again, Clarkson and Woodruff's paper is the first one to talk about this in the context of randomized linear algebra. And then there's been a number of papers in the theoretical computer science community that build upon their work. But one thing to note is there's never a stability analysis in some sense because it's a very numerical analyst thing to do. And also, it's not very clear that what the complexity is going to be like if you do this in those papers. Well, and in particular, it does look like you do need this orthogonalization cost, or maybe it's not orthogonalization, but you need m times r squared cost. And once again, these people read a paper involving the QR factorization that aims to stabilize this method. I'll maybe mention that just because you are using QR factorization and the inverse is a well-conditioned matrix doesn't immediately imply the stability of the method because they're using Q matrix essentially explicitly. And then QR factorization itself is an ill-conditioned operation in the sense that the exact Q versus the computed Q might be very different. Of course, QR minus the matrix is going to be small by backward stability of QR. But anyway, so it is strictly speaking an open problem to show this method is backward stable or just stable, although I strongly believe it is. But anyway, so the focus of this work is to go back to the simpler expression in some sense, or at least simpler or cheaper to evaluate, and then show that it's going to be stable or if implemented in an appropriate way with the pseudo-inverse, epsilon pseudo-inverse. There's a small modification that we do need to do. And the benefit of doing so is the cost becomes near optimal, at least for dense matrices. And I believe for many classes of matrices, just because of the simplicity of the algorithm. So here I want to kind of summarize or get an overview of a comparison of methods for randomized SVD. And in terms of well, stability, speed, and sometimes or many of these methods can be written in this general form that I kept showing you. And HMT, for example, is right here. And in terms of the cost, so what I'm claiming here is the stabilized generalized Nystrom is essentially optimal, and then it does, in particular, it does not contain this orthogonalization cost. So it will be very attractive, especially when the rank is pretty large. So if the rank is like square root of n or larger, then this blue term, so mr squared term, can be the dominant part of the computation, and that's where we don't have, and that's where we can potentially outperform the competitors significantly. And in terms of stability, so this is, I think, the first one to have a proven backward stability. The rest usually perform well, actually, but so these crosses mean there are cases where it actually becomes unstable. These check with a parenthesis means there's no proof, but I personally think it is stable. So it's conjectured to be stable. Yeah. Okay. So a final thing to note maybe is not only do we know the order, the complexity in the big O sense, we also know the constants because it's such a simple algorithm. And then the constants here are actually reasonably small for the generalized Nystrom method. Okay, so this is a very good point to stop and pause for questions because the rest will be a little bit technical. Is there any questions on?
Yeah, there are questions
yeah.
already in in Zoom. So there is a question from the beginning of your talk. Rosemarie Renault was asking whether Y is random. I guess we already answered that. The Y matrix.
Y matrix.
Yes.
Yes. Y is another, right, but I probably didn't emphasize this. Y is a random matrix that is independent of X, and this independence is quite important in the analysis.
Okay, another question is, this is just a comment by Jelani Nelson, saying that reference paper is 2013, not 2009. That was another paper.
Okay, right. I see. You mean Clarkson Woodruff. Okay, yeah, that might have been theirs.
Okay, so there are two more questions from Jianlin or Jean. Okay, the first question is, the dominant cost big O of M and R appears both HMT and Nystrom due to the math-vec. Can you please explain why Nystrom is much faster even for small r? This first question.
You mean here? So Nystrom, what does it need to do? So HMT requiring M and R is reasonably clear, I hope, because you have to do. So this is really coming from this multiplication. This is where you need M and R operations. Even if you take X to be a structured matrix. And Nystrom, why is it so fast? It's essentially fast because all you have to do is compute AX, and then you have to compute this. And in some sense, that's all you have to do. So in order to compute this whole matrix, yes, you have to involve like M and R square cost. But for practical purposes, once we have these factors, for example, you can do an operation with this approximation. For example, you can multiply that approximation to a vector by just let's call it V, right? So taking this times V, and then doing this pseudoinversion times V, that will be a linear system, and then do this matrix vector multiplication. So that cost will be, I think, M times R, if we got it right. Yes. So once you have all these two factors, basically, or three factors, you already have the approximation. So I call it done by that point. And that's why Nystrom is so much faster.
Okay, the second question by the same person is, this is the following. The standard Nystrom method seems to just take AX to be a sample of some columns of A. Would it still be able to achieve high accuracy?
Great question. So yes, I think the classical Nystrom was doing exactly that. So you just take X to be a subsample columns of the identity. And so it will work, provided that A is so-called incoherent. So basically, in other words, the so-called lever scores are all low. So basically, if the singular vectors of A are sufficiently randomized, then just extracting a few columns. So basically, that would work beautifully. The idea is that by using randomization, we don't have to make that kind of assumption. And in this near optimal approximation quality is going to be guaranteed for any matrix A. So assuming low incoherency is something that we want to avoid in this work. And that's why we need to do a randomization or actually structured randomization. So otherwise, that kind of approximation is going to work just fine.
So one more question from Catherine Lund. Have these methods been used already for generalized matrix functions? If so, do you know how they compare to established approaches?
Generalized matrix functions, or just matrix functions? So the quick answer—
Generalized matrix functions. I can confirm they exist.
Okay, so Nystrom, I don't know, but I do know, like, for example, Daniel Kressner and his collaborators have been working on like lower rank updates of matrix functions. And then I think they do use HMT, for example, in the computation.
Hello, I know Michele Benzi and collaborators have been working on generalized matrix functions.
Oh, yeah, in terms of the SVD function. Oh, I got it. Okay, yeah. I think I got what you mean. So involving the singular vectors, and then inside the singular value matrix, you have the functions. All right. So I don't know if this has been used, like Nystrom or generalized Nystrom. Generalized Nystrom, in some sense, is a relatively new thing. So I'll be very glad to see if this will work there. I have not tried it myself.
Okay, so I leave it to Melina.
There are no questions on YouTube yet, just a hello from Nicolas Bourmal.
Hello, Nicola. Okay, thank you very much. So I guess I move on. Look at the time. Okay, so so from here I start doing the technical analysis of the method. So two things need to be shown. First, that the generalized Nystrom approximation is going to give you a near optimal approximation in terms of the low rank relative to the best possible low rank or approximation. The second thing is actually more numerical analytic. We look at the floating point errors incurred in the computation of the pseudo-inverse and show that even in the presence of random errors, what you get at the end is going to be a good approximation. Okay, so before we get started, I wanted to kind of talk about a very important result in random matrix theory. Not that I'm an expert in random matrix theory, but to me, this is the most important result in random matrix theory. Well, important in the sense that it's very, very useful for numerical linear algebra. And this is called Marchenko-Pasteur distribution. And what it concerns is it's about the singular values of a random matrix in an M by N, where all the entries are, well, let's say just the normal IID, standard normal distribution. It doesn't have to be normal. It can be, as long as it's identical, independent, you have a similar result on the distribution of the singular values. And here it is. So basically, it tells you essentially the PDF of, or the density of the singular values distribution. And what's very important here, for at least for this work, is that the support is specified to be between a square root of m plus and minus n, or plus and minus square root of n. And the consequence of this is that if you have rectangular random matrix, then essentially there is no way that it is rank deficient. It has to be well conditioned. Well, because the singular values, the smallest one is essentially bounded from below by square root of m minus square root of n. So all the singular values are captured essentially in this interval. One immediate consequence is that the condition number is, well, can be estimated, and this is a relatively sharp condition number estimate to be this. So if you think of like the aspect ratio being like 2, so like 2 million by 1 million random matrix, let's say, basically the condition number of that is going to be something like 3. I don't know the exact number, but it's definitely never going to be like 100 or larger. So that's a very well conditioned matrix. And then the higher the aspect ratio, the more well conditioned it becomes. Well, in some sense, you know, if you have two random vectors, by central limit theorem, they're going to be essentially orthogonal up to like 1 over square root of n. And this is like a more sophisticated version of that. And I personally think this kind of underlies the theoretical backbone of many of the key developments in computational mathematics that's been going on in the past decade or two. So here are the list of my favorite examples. For example, compressed sensing ORP is very much about like the condition number of a tall, skinny random matrix. And of course, randomized SVD, I'm going to use it. Blended pick is another very successful line of work in randomized linear algebra. This is for least squares problems. But yeah, I think this is definitely one of the results that is well worth knowing for any applied mathematician. So, for the purpose of this talk, please be aware that if you see a random rectangular matrix, that's going to be well conditioned with extremely high probability. So I am going to start with my analysis. Once again, I start with the general form like this. So this includes HMT and of course generalized Nystrom, among others. And then the key fact is that it can be written, this can be written as a matrix, the original matrix times a projection. And then another, well, it could be also written as projection times A. Where this projection is this projection. So you can immediately see that this is a projection because you square it and you get it itself. So this probably was in the front actually, so that might have been a typo. But an immediate consequence is that the error can be written, so this is correct. So as identity minus a projection times A, and because it's a projection from both sides, if you will, you can write the error in many other ways. But what I'm going to do is I'm going to start with this expression. And this expression is already very useful in the sense that now I can squeeze in a matrix of this form to the right, where M is any matrix, and this equality holds. The reason being that this times AX is 0, almost by definition, because this is a projector onto the column space of AX. So what I'm going to do is I'm going to choose M to be a specific matrix in such a way that this expression is going to tell you that this error term E is going to be small. So the choice of M is going to be the crucial part of what's going to follow. Let me start with HMT because it's such a popular method. So once again, here we choose Y equals AX, and then this becomes an orthogonal projector. A nice consequence of which is that the projector has a norm 1 in the spectral norm. Once again, the error is this. So we can just immediately bound it by this because this has norm 1. So here's where we choose M. I'm going to choose M to be equal to that matrix. The rationale underneath this is this way we get another projector. It's an oblique projector. It's not an orthogonal one. And the row space here is V, where V is the top R hat singular vectors of A. So R hat is a smaller number than R, so we get to choose whatever R hat we like. But if we do so, we get this nice property. And therefore, so we're looking at this matrix, which is the error matrix. We can now squeeze in this matrix because of this nice identity without changing the matrix. The beauty of which is that now this matrix becomes a small matrix because we're projecting out the dominant parts of A by this orthogonal projector. So this will become just the matrix of singular values of the smaller ones, so R hat plus 1 and onwards. So now the argument boils down to just using standard matrix norm equalities to this. So this is a matrix that we like because it's small. This is a matrix that we are not sure yet. But here is where we're going to use Marchenko-Pasteur, which tells us that rectangular random matrices are well conditioned. And that's essentially all we need to know in order to see that this is going to be a nicely bounded matrix. Essentially, this is just a random matrix. The norm is not too large. The only concern is the pseudo-inverse. But this matrix is rectangular because we're taking R hat to be smaller than R. So therefore, as an immediate consequence, you have essentially an upper bound or upper bound that holds with high probability for this. And then, well, this doesn't depend on the condition number, for example, of A or the smallest singular value. So you can think of it as an order 1 term. If you're picky, then you might say the presence of the square root of n is annoying because M and N are large numbers, or I'm happy to take to be much smaller. So this may or may not be satisfying. So in that case, there is a way to work a little bit harder to get a better bound. So once again, this is the optimal possible. This is the extra factor that you need to tolerate. And then I am here. We're recovering the theorem derived in the HMT paper. Using a little bit more elaborate analysis. But I still think this is a lot simpler than what's previously been written in the literature. So we need to use some properties of Gaussian matrices. So here I'm assuming X is Gaussian. And then, for example, this equality uses heavily the fact that it's X is a Gaussian matrix. But then you get a precise bound. And now we don't have M or N in the constant, which is very good news. Okay, so I turn to generalized Nystrom, which once again is a version that takes X and Y to be independent and Y to have a little bit more number of columns than X. And then I start with the same expression of the error. I squeeze in this factor, which I can do, and then I'm going to choose M to be actually the same matrix. So then we get this bound for the norm. The slight difference here is that this is no longer an orthogonal projector. Therefore, the norm is not always equal to 1. or actually it's bounded from below by 1. But we can just split out this term, this bound norm into two terms. The first term is just nothing else than HMT. The second term is HMT times another projector. But how do we bound? So it boils down to bounding the norm of this projector. Once again, by Marchenko-Pasteur, this projector, because it involves basically Gaussian matrices or random matrices, and it's going to be rectangular, the norm is going to be bounded by an order 1 term, or maybe order square root of n term with high probability. And so that's essentially an intuitive way to understand why this works. So in essence, it's this generalized Nystrom approximation is going to be essentially a constant times worse than HMT. So if the best low rank approximation is converging exponentially, for example, to that of A, then that factor can be negligible, and then you still get a very good low rank approximation. So just like in HMT, we are able to work a little bit harder to get a much better bound. So this is a much tighter bound than before in the sense that there's no square root of n or m. And L is, just to remind you, L is the oversampling factor, so which I'm going to take proportionally to R. So you can actually see that this is going to just be bounded by a constant. So let's assume, for example, L is equal to R, then this is essentially just 2. So this will be like square root of 3. So we're really only a constant factor away from HMT. And so here's the analysis that I guess I wouldn't go into details. Actually, this just because generalized Nystrom is exactly the same approximation used by Tropp and his co-authors in this 2017 paper. So this bound turns out to be the exact same as their bound in their theory. Okay, so this is where I start talking about like the stability of stabilized generalized Nystrom. So this is a slightly different algorithm, right? So because we're introducing this epsilon pseudo-inverse into the expression. And this becomes a little bit tricky because the goal really is to evaluate or examine what will happen if you compute this in finite precision arithmetic. So we really have to take care of this pseudo-inverse or this epsilon pseudo-inverse. And then we have to talk about how it's going to be implemented and what is the round error going to, how is that going to play a role in the computed result. So in order to do so, I'm going to take 2 steps. I'm going to first consider another approximate of this form where the core matrix is slightly different. So instead of A here, I'm going to take an A tilde, where A tilde is a matrix that is close to A, but it's a slight perturbation. But I'm going to take the perturbation to be essentially epsilon's a very small number, like order machine precision. Then I claim that with this expression, you still get a good approximate. It's still a low rank. It's still rank R, but we can show that the approximation quality is in the same order as generalized Nystrom without this epsilon pseudo-inverse or without this perturbation in the matrix. The second thing that I'm going to show is that with the computed version of the stabilized Nystrom, generalized Nystrom, you can write the computed result exactly as a realization of this for a certain or for some A tilde that is close to A. So it's like a 2-step algorithm. So number 1 has nothing to do with floating point arithmetic. Number 2, we try to squeeze in the error. It's going to be the backward error incurred in this pseudo inversion, and try to represent that as a perturbation in the matrix, in the core matrix, and then show that using step 1 that everything kind of gets together and you get stable result. So this is the overall claim that I make at the end. So with the computed version of stabilized generalized Nystrom, you still have basically something that is close to the error of HMT up to this constant, which isn't too bad. So there's no square root of m or n once again, so it's good in that sense. There is an epsilon term, which I guess it's natural because we're introducing some epsilon pseudo-inverse here. But of course, the assumption is that epsilon is in the order of machine precision, so that's never an issue. Okay, so this is the theorem that I'd like to claim. I am conscious of the time. So in order to show these, so this is a sketch for the first step where I show that this matrix is going to give you a reasonably good approximation to, or I guess this matrix to A. And then we're going to rely on three facts, Marchenko-Pasteur once again. And then these are technical results that I'm not going to be able to show you here, but please look at my preprint if you're interested. So we start with this approximation of stabilized generalized Nystrom. Using the third result, we get this. So basically, the problem here is that this matrix is no longer an exact projection because of this tilde here, but it's still an approximate projection in the sense that you still get this. So we use that in order to rewrite the error to be of a similar form as before, plus an epsilon. And then we use the same technique basically in order to bound what we have here. Now we use Marchenko-Pasteur again, along with this fact to show that this is also bounded by a constant. Basically, this red guy is a constant times the norm, the error norm of HMT. So that's the first step. The second step is where we rely on a classical result in the stability analysis of numerical linear algebra. And then, of course, there's this beautiful book by Nick Hayam. And this is basically, I use one of the results in that book to talk about the error, or actually the backward error, in solving an underdetermined linear system. So it's not exactly trivial to see, but this in order to evaluate this, you need to solve an underdetermined linear system, and you need to solve many of them actually. But let's suppose we use the SVD or QR to solve that. And then you get a beautiful backward stability result that says essentially the computed result is going to be the exact solution for a slightly perturbed matrix. So I'm going to call that M, so M plus epsilon. So epsilon, it represents the backward error in the solution for this underdetermined linear system. And so then I can just basically, so M, it was defined this way. So I put it back in the expression for the computed version of the generalized Nystrom expression. So FL means floating point, and then this the big bracket means the ith row. And what I'm trying to show here is so these red matrices are essentially the same matrix. You end up with this expression, which is exactly the expression that I had in 2 slides ago right here. And then this is the expression that I showed separately, that it's going to give you a good approximation comparable to generalized Nystrom. So this is how I get a stability result even in the presence of floating point arithmetic errors. So that's the technical part of this work. I guess one thing I might want to emphasize is here a key fact in what's going on here is that even if you have a linear system that's ill-conditioned, if you know that the matrix and also the solution, the key is that the solution has order 1 norm, then you actually see that the residual has to be in the order of epsilon with the computed x hat. So this fact is not necessarily true, especially if the norm of x is huge, which can happen if you have a ill-conditioned linear system. But here we're really using that fact because of the strong structure that the linear systems that we're solving possesses. Okay, so I'll now turn to some experiments. So first of all, dense matrices, 50,000 by 50,000. Now it's no longer symmetric. So that's the difference from before. And so essentially, generalized Nystrom is like 10 times faster than the HMT, for example. And then the accuracy of it is actually identical up to an epsilon term to Tropp's these people's work. So it's a really fast algorithm with very good accuracy. So I wanted to also show you an interesting experiment. So randomized linear algebra, I think the common understanding is that it should be used when the rank is very low. So if the rank is like 10 or something, by all means use randomization. But if the rank is very close to M or N, then I don't think randomized SVD has been used very often. But I wanted to see if, where the break-even point is in terms of the speed and accuracy. And here's the answer, which is kind of curious. So so here is a 30 by 30,000 matrix for which an SVD is possible with like 2,000 seconds. So these methods, which are randomized, are doing much faster than the full SVD. So this is like much more than 10 times faster with GN. And of course, they all do well in terms of tracing the actual singular value decay. So at least from this experiment, it seems to me that whenever it makes sense to do a low rank approximation, it is worth doing a randomized SVD rather than a full SVD if speed is a concern. So one more thing, I guess, through experiments, I did mention that you need to take the oversampling parameter L to be proportional to the rank R. Why is that necessary? So I wanted to show you some experiments. So here I'm taking a matrix to have a slowly decaying singular values, and then take different values of the oversampling factor. So this is constant oversampling, oversampling proportionally to R, like massive oversampling 5 times R. And then the more that you oversample, the better you get, and in some sense, the closer that you get to HMT. But if you take your oversampling to be a constant, then what happens is that depending on the decay of the singular values, your method may, or the generalized Nystrom may not even converge. So that will be really bad news. As opposed to if you take L to be proportional to R, then it always is guaranteed to essentially trace the decay of the singular values. And it really makes sense if you look at, if you go back to the error bound that we presented. So there's the error of the HMT missing here, I think. But so basically, this is the constant by which we might do worse than HMT. So we would like this factor to be a constant independent of R. So a good way to achieve that is to just take L to grow with R proportionally to R. Of course, when the singular values are decaying much faster, then this is not as important to oversample proportionally. So depending on how much time I have, which I don't have too much. So I did want to mention a little bit about another application of generalized Nystrom, just because it's just such a simple algorithm. It's good for other purposes also. And one thing I want to highlight is to update a matrix. So suppose that you, for example, you might have like an additional factor in the matrix, or additional perturbation in the matrix. You might also have like appended matrices. So you start with A, but you like to kind of add E at the bottom or to the right. So these stuffs are much easier with generalized Nystrom than other methods. Because all we have to do is essentially to find what will happen to these factors. And then in order to compute those, all we have to do essentially, for example, so appending a few columns, all you have to do is just compute these guys, so the red guys. And they only involve the matrix E. So you don't have to revisit the matrix A to achieve this, which I think is a great benefit of this approach. And also, you obviously don't have to orthogonalize that whatever that you computed. So updating this matrix is going to cost you much less than other methods. So so here's an illustration in terms of the speed and accuracy, I guess, of trying to append a matrix to a sparse matrix, I think. So we're getting like 20 times speed up. I think that's the end of the experiments. So that concludes my talk, basically. So I would like to advertise this expression for low rank approximation, which is fast and numerically stable. And especially when the rank is much larger than 1, this is going to be an attractive method for low rank approximation, I think. Yeah, so I guess the key component is really a classical result in numerical linear algebra for the stability proof of the method. I did skip a few details. Please take a look at this archive preprint if you are interested. So thank you very much. I would love to take more questions if there is any.
Yeah, there are a few questions actually in Zoom. So the first question is from Daniel Kresner. He asks, how difficult would it be to derive tail bounds for the error?
Right, so that's an excellent question. So so I have not worked out the details, but it is going to be possible. So for example, HMT has a beautiful tail bound, and so a bulk of their theoretical analysis depends on, is about getting tail bounds for so high probability bounds for the error in HMT. With generalized Nystrom and stabilized version, I don't think it's been worked out in the literature. One thing, but you can do that. So I think we're going to have to assume you take Gaussian matrices as the sample matrices. But for example, you can, so Marchenko-Pastor, or there's a follow-up work by Davidson and Zarek, which says that the probability of a random matrix like this having deviation, so having a small singular value strictly smaller than this by, say, t, is exponentially small with t, t and the dimension, I think. So we can use that in order to bound, for example, bounds like this. This is probably not going to work, but so you can bound this term carefully using the Gaussian Gaussian assumption together with such bounds to get like probabilistic bounds. So once again, I haven't worked it out. I'll love to work with somebody to get such bounds. But yes, it's been so far only about the expectation. I strongly believe, I'm almost certain that there will be high probability bounds that says that with exponentially high probability, anything that the probability of getting anything that's like 10 times larger than this is going to be exponentially small.
Okay, yeah. So more questions here. Rosemary Renault, are the results improved in the same way when power iteration is included, proofs of stabilization, etc.?
Right, so that's another excellent question. So there's a beautiful paper by Minggu, I think I cited here, that uses power method, essentially subspace iteration. So instead of doing this, we're going to take like powers here. In other words, you can say this is the x that we're going to take, for example. It will be much more expensive just because you really need to revisit the matrix. So for example, I didn't emphasize this probably enough, but it is very practical to take x and y to be like subsampled parts of the Fourier matrix. That way you get this mnlog n complexity rather than mnr. So once you do power iteration type steps, you really need to do mnr operation, at least as far as I know. So in terms of the speed, it will be less attractive, but you do get benefits in terms of the accuracy. So what happens essentially is that the dominant singular values will be much larger relative to the rest because of the powering. So yes, the error bound will be improved. The cost will be significantly higher.
So another question by Osman Malik. If singular values are not decaying exponentially, is the gap between the SVD and the randomized methods on for instance, page 17 of roughly the same size?
So if the singular values are decaying slower, then I'm not sure I completely got the question, but
so in this case,
yeah.
Is the gap between the SVD and the randomized methods roughly the same size?
So yes, I would like to claim yes, but in some sense, HMT, there is no flexibility in some sense. So HMT is fixed here, but generalized Nystrom, there's this oversampling parameter that you get to choose. Here, I'm always choosing it to be R over 2, so 0.5 times R. If you choose that to be like larger, like 10 times R even, so then you get really something close to HMT. On the other hand, if you take the oversampling factor to be smaller, it's like this is a constant where you really deviate from the rest. So this is not recommended. These are all recommended. So you would want to oversample as much as reasonably possible, I guess. But a 0.5 R is a cheap but a stable method, more choice.
Okay, one last question from Zoom. Can your method be used to solve least square systems for which a moderate norm solution exists?
That is an excellent question. So, so that's not immediate from this work. I have been thinking about that, and I think there's a way to do it. So, yeah, maybe I'll stop here. So, yeah, yes, that's a promising direction to pursue.
Okay, I'm done.
Thank you.
Okay, hello from YouTube. There was one question which you already answered, so I think we can finish. Thank you.
Okay.
Okay. I think it's back to me. Thank you, Yuji, for this nice and exceptionally clear talk. I think I will just pull up the slide of our seminar. Yes.
Let me stop.
Okay. Yes. Good. So yeah, this one. Good. So thank you, Yuji, again. Thanks to everybody for this lively discussion. We look forward to continuing with our ENLA seminar series on November 11th. So that's in 2 weeks with Des Hayem. And then we will go on November 25th, François Tisseur, and December 9th, Gen Greif. So goodbye for today. And please stay healthy and see you then. Bye-bye.